Good morning, everyone. So, I am Dr. Satish Kumar Gurupatam, and today I'm going to present the frequency variation of particle oscillations due to temperature of liquid in spontaneous dispersion. So, I want to mention my students Navveet, Ashton, and Daniel from Kennesaw State University have worked on this project. So this is how I have organized my presentation. So in introduction, I'm going to show you what is spontaneous dispersion of particles, and later I'm going to show how the particle is absorbed at air-liquid interface, and how this spontaneous dispersion takes place, and I will explain my experiment in which we have measured the variation in the frequency of the particles due to the temperature difference of the liquid, and I will show the results, which will be followed by the conclusion. So I'm going to show this video where you will watch the sand particles spontaneously dispersing on water surface. So you can see that the sand particles, the moment they touch the water surface, they immediately disperse, and later they come back to form a cluster. They disperse very fast on the surface. Later, they form the clusters. So this is because the surface of the water is deformed by the particles absorption. And I'm going to show another video for the same phenomenon. So here we are seeing the weak particles getting dispersed on water surface, and so you can see that it is more like a firework, and so at various time intervals we are seeing the pictures. So here it's more explosive than the sand particles that we watched in the previous video, because the particle size is almost 2 to 100 micron. So one last video I'm going to show you again on this phenomenon. So here again we are seeing the green color sand particles, and the size is definitely bigger than the bit particle size, almost 200 microns, and you can see that the dispersion rate is lower than the wheat flour one, and this is at different time intervals. So if we drop a mustard seed over the water surface where we have very small, maybe 20 micron sized glass particles, you can see that there is a space created surrounding this mustard seed when it touches the water surface. So basically it drives away all the smaller glass particles away from the mustard seed. And I'm going to explain how this takes place, this whole spontaneous dispersion of particles. So let's consider one particle. So when the particle comes in contact with the liquid surface, so basically it is pulled by the capillary force. So you can see that the capillary force is acting downward in this configuration, and once it is pulled in, and when it overshoots the equilibrium height, so equilibrium height is nothing but the center of the particle and the from there the distance until the undeformed liquid surface. So basically if the particle is sitting here, this equilibrium height is going to be equal to the radius. So when that particle center overshoots the equilibrium height, at that time, so you can see that the interface is going to be something like this, and now the capillary force component is going to act upward. So because of which the particle will try to go up, and this continues for a while until the particles becomes stable by the uh, viscous force that will be acting on the particle. So what happens is this oscillation up and down induces a flow on the water surface and liquid surface, which drives away the surrounding smaller particles. And so the forces which are acting on the particle when it is in touch with the liquid interface. So the first one is going to be capillary force, and the second one is buoyant force, obviously weight of the particle, and the drag force, which will be acting against the movement of the particle. So if we sum up all these forces, that will be equal to the mass times acceleration of the particle. And for our calculation, the capillary forces were considered using these models. Okay, and so when we solve this equation, we can obtain the initial velocity of the particle when it touches the interface. So this is what the mathematical expression we have. Here, more importantly, we can see that the radius of the particle is sitting in the diameter, in the denominator. So when the particle size is reduced, the velocity is going to be increased. That's the whole point of looking at this equation. And so here the parameters: interfacial tension, viscosity of the fluid, effective fluid density, particle density, and so we can see that when the particle size is reduced, the velocity, the initial velocity is going to be very high, and a particle of the particle size of diameter 200 millimeter can accelerate to 1 meter per second, and whereas 10 nanometer size particles such as a virus or a protein molecule may accelerate a velocity of around 40 meter per second. So that is the reason we saw the very explosive dispersion of the particles. And so I also mentioned the particle used to oscillate, and we can find out the frequency of that oscillation using this mathematical expression. Again, what we are seeing here is when the particle size is going down, the frequency of oscillation is going up. And the same is true when two particles are coming in contact with the liquid surface. Both undergo this oscillation, and which basically induces a flow, and the flow moves the particles away from each other. And when we increase the number of particles, and the velocity with which they are moving also increases. That's what we are seeing here. That is the reason when we have more particles, the dispersion is very explosive. And we wanted to find out the variation of the frequency of particle when we change the liquid surface. So this is our experimental setup. So we used to have a camera setup on the top, and this is the petri dish, and we had to basically water with different temperatures, and we drop the particles. We basically consider just one particle, though we are showing multiple here. And that video was recorded and analyzed. So you can see that the oscillation of a 3 millimeter size bead at different time intervals on water at 30 degrees Celsius. From the picture, you can see that the particle is, when it is coming in contact, it is pulled into the liquid, and it is reaching a maximum height, and after that it reverses its direction, it goes up, and again it comes down, and finally it settles down. So these are the different frames from the video taken. And when we change this temperature of the water surface, the same phenomenon takes place, but you can see that it is slowed down, so it takes more time to reach this, at least to complete one cycle. So it takes 0.283 seconds here, whereas here it was 0.15 seconds. And so when the water temperature is 60 degrees Celsius, actually. So we plotted the frequency. So on x-axis we have time. On y-axis we have z over r, where z is the equilibrium height, as I mentioned before. R is the particle radius. We took this ratio basically. So you can see that. So with higher temperature, it is taking more time to complete one cycle. And so this is how the particle is going in and coming out. We basically measure how deep it is taken inside. And here are some conclusions. Small particles, when they come in contact, they disperse very explosively. So virus, proteins, those kind of very small particles may reach 47 meters per second, which is huge. And so in the experiments, we basically change the liquid temperature. So it shows that um, it changes, basically the frequency of oscillation changes. This occurs because the magnitude of capillary force that the particles experience decreases due to the increased temperature of the liquid, which in turn decreases surface tension of the liquid and thereby the capillary force. Though the drag force experienced by the particles might also vary due to the change in temperature of the liquid surface, here the influence of the change in the capillary force dominates the phenomenon, which leads to the decrease in the dispersion rate. So that's what the conclusion we would have. Thank you for your patience. Let me know if you have any questions.